Let's set up the null hypothesis, which is simply that each group looks like a random sample from all 15 balls. So you can just say that the 4 Colts footballs are like a sample drawn at random from the 15 balls, which means that the 11 that are left over are also a random sample. The alternative would say, not really. The drops in pressures of the Patriots balls are too large for the 2 groups to look like random samples from the 15 balls. The natural test statistic is the difference between the averages of the 2 groups. We calculated Colts minus Patriots. The alternative says that the Patriots drops are larger, so that difference was negative. And so negative values of that difference favor the alternative. How do we simulate the statistic under the null hypothesis? Well, we have 2 groups. We have the Colts and the Patriots. If both look like random samples from 15 balls, then it shouldn't matter which 4 balls are called Colts and which are called Patriots, so we will randomly permute all the 15 balls. We will label 11 of them Patriots and the remaining 4 Colts, and then we will look at the difference between the averages of the 2 groups, Colts minus Patriots, of these shuffled groups. And then we'll do that over and over again. That will be the prediction under the null hypothesis, which we will then compare with the actual difference that we observed. To do this, let's start by organizing our calculation. So we'll create a new table of group labels. And a table consisting of the drop values. What we have to do now is shuffle the drops and extract the shuffled drops as an array. Then we will create a new table that is the table of the original group labels that we just created, augmented by the shuffle drops. These are our shuffle data. We will figure out the means of the 2 groups in the shuffled data. So we'll take shuffled table, we will group by team, and we will ask for the average drop in each of the 2 groups, and those averages will appear in column 1, so we will extract column 1 as an array, and so means is an array, and our new difference that we observe will be means item 0 Colts minus Patriots, and we will take a look at this difference. You will have noticed, I'm sure, that this is exactly the same as what we did with the birth weights of the babies of the smoking and the non-smoking mothers. Let's see if this works, or if I've made an error somewhere. I have made an error somewhere. What's the error? The name drop is not defined. Yes, indeed, it is not defined. much better. Got minus 0.53, right? Okay, well, let's see, instead of running the cell over and over again, let's see what the null hypothesis predicts. We will run our simulation starting with an empty array. Let's do a whole bunch of repetitions. This is a small table. We should be able to do a lot of repetitions. What are we going to repeat? We are going to repeat the calculation of one value of the test statistic under the null hypothesis. That's this cell. The only difference being we don't want to look at the statistic we created, we want to append it to our collection array. And let's try running that. Takes a little while. I hope not too long. What we're going to do is draw a histogram of these differences and compare with the observed differences that we got. I was perhaps a little over-ambitious trying to do 20,000, but it's done, and I am going to collect those differences in a table and draw the histogram using a cell that I typed in earlier, and the differences look like this. The red dot corresponds to our observed difference of approximately minus 0.7. This distribution is a prediction under the null hypothesis. It predicts what the difference between the two group means if the two groups were just like random samples from all 15 balls. That is why the center is at 0. If the two groups are like random samples from all 15 balls, then on average the drops in pressure should be the same, and so on average the difference should be 0. This is the prediction of the test statistic under the null hypothesis. This is our observed test statistic. It's looking a bit far out in the tails. The difference that we computed were Colts minus Patriots. The alternative says that the Patriots drops are larger, so Colts minus Patriots is negative. So for the p-value, we should look at this difference and below to see what proportion of our simulated values were at the observed value or below. So np.count non-zero. The array is called differences. Those are our simulated values. We want to see how many of them were less than or equal to the observed difference. We just decided why we had to look at this side, because that's the side that favors the alternative. And then we want to convert this count to a proportion out of the number of repetitions that we did, which was 20,000. And that's the p-value, 0.003. So that's 0.3 of a percent. That's a pretty small p-value. And so we have to conclude that the data support the fact that the Patriots drops were too large for the two sets of balls to look like random samples from all the 15 available balls. Is this an indictment of the Patriots? All we have done is establish that the two sets don't look like random samples from all 15 balls. The test never answers the question of why. but it was why that was of key interest to especially the Colts and also to the rest of the football world. It's important for us when we carry out a test of significance to recognize what it says and what it doesn't say. This test does not say that anybody was cheating. It does not give any reason. It just says that based on these data, we should not be concluding that the two sets of balls look like random samples from all of the 15 balls. The NFL had an independent investigation done. It was very thorough, involving physicists from major universities and a lot of careful data analysis. That report is available to the public, and there is a link to it in your textbook. You're welcome to read that. For now, just note that we have learned how to do A/B testing, that is to see whether two samples look like they have been drawn from the same underlying distribution or not, and that the method applies in a variety of different contexts.